hoping my batteries, my mic hold up. Okay, so yesterday we were talking about end behavior, right? So we said a couple things. We said that we can use the leading term, thank you very much. We can use the leading term in the polynomial to determine the end behavior because the leading term is the dominant term for large values of x, large positive and negative values of x, right? So if the leading term matches one of these power functions, we know that the end behavior is going to be the same as our parent graphs. We went one step further and just said something like this, right? We know that the leading coefficient test just tells us that if the degree of the polynomial is even, if the leading coefficient is positive, we get positive even behavior. If the leading coefficient is negative, we get negative end behavior, right? Negative even end behavior, right? If the degree of the polynomial is odd, for a positive leading coefficient, we get positive odd behavior. Negative leading coefficient, we get negative odd behavior, right? And that's pretty simple, right? That gives us the end behavior very, very simply. Okay, so now here's where we kind of left off. We're going to go a little further than just end behavior today. We're going to talk about things like turning points and the nature of the zeros of polynomials. And this, I think this is really pretty fun stuff. I think you should think this is fun too. We're going to be able to sketch polynomials based on the stuff we're told today. It's like doing a puzzle. I mean, it really is. It really is. You'll see what I mean. It's fun. It is fun. So the points at which a polynomial function switches direction are called the turning points, right? So for example, on this little sketch right here, that's a turning point and that's a turning point, right? Places where it changes direction. So in other words, if an ant is walking along the graph of the function in the positive x direction from left to right, a turning point would be where the ant changes from increasing, meaning walking uphill, to decreasing, walking downhill, like this guy right there, or changes from decreasing, walking downhill, to increasing, walking uphill. So those always end up looking like turning points on a graph, on a polynomial graph, always look like peaks or valleys. It's like the ant is walking over a peak or through the bottom of a valley every time. If the turning point is higher than any nearby point, then we call it a relative maximum. If the turning point is lower than any nearby points, we call it a relative minimum. So on our graph, the relative maximum would be the one right there. See that? Okay. Why do we call it a relative maximum? Well, because it may not be the highest point that the ant could ever go to. We'd call that an absolute or a global maximum. But relative to the terrain around him, it is the highest point, like a peak, right? If you're standing on a mountain peak, you might be able to look out and see a taller peak over there, but you're still on a peak because relative to the ground around you, you're at the highest place. That makes sense? Okay. A relative minimum, on the other hand, is going to be like that point right there. How come? Because it may not be the absolute lowest point on the graph, but relatively or locally speaking, it is. Okay. Bottom of a valley. Yeah. Okay. Makes sense? Give me thumbs. That'll make sense? Okay. So maximum and minimum values are called extrema, which is just the plural for extremum. A single maximum or minimum would be an extremum. Okay. Meaning just like something that's extreme. Extreme maximum or extreme minimum, meaning, peak or valley. Turning points define where the function is increasing or decreasing, right? Because those are the points of transition. On this graph up here, the ant is increasing to the left of the maximum, agreed? And the ant is increasing to the right of the minimum. But the ant is decreasing between the two, right? Extrema are places where the function transitions from increasing to decreasing or vice versa, Okay? Another important relationship we have to consider. A polynomial of degree n can have at most, what do you think? How many turning points? If it's an nth degree polynomial, what's the maximum number of turning points? And I'll give you a hint. You can't pick a specific number here because the degree could be 1,000 and it could have all kinds of turning points. No, not infinite. But if the degree is n, which is a whole number, so if the degree is n, then how many turning points could you have? Not n. I'll give you an example. Because think about, what if the degree is 2? What does the graph of a second degree polynomial look like? It's a parabola, isn't it? Right? Okay, so if n is 2, that's a quadratic function. It's got a parabola. How many turning points does a parabola have? 1. It's only got either a maximum or a minimum, depending on whether it opens up or down, right? So if the degree is 2, but it only has 1 turning point, what do you think the answer is going to be? If the degree is n, how many turning points could it have? N minus 1. Yeah. Okay. Right? So an nth degree polynomial could only have at most n minus 1 turning points. The number of turning points, the maximum number of turning points, is always 1 fewer than the degree of the polynomial. Okay, so now let's talk about x-intercepts. The points at which real zeros are the points at which the function intersects what? Real zeros. Real zeros always correspond to what graphically? X. Well, the x-axis is that's a set of an infinite number of points. But I want to know, real zeros of functions always correspond to what on the graph of the function? No. No, real zeros. Those are the places where the function is equal to what? 0. Okay, well, where the function equals 0, if those are real numbers, right, where would those have to be in the xy plane? Not on the y-axis, on the x-axis, right? Places where the function equals 0. Is that what you were saying? Okay, but we haven't said what the name of those are. The name isn't the x-axis. What do we call the places where the function crosses the x-axis? X-intercepts. See what I'm saying? Okay, right? So x-intercepts, real zeros, you got to get that one kind of just cemented in your brain. Real zeros always correspond to x-intercepts. Now, imaginary zeros do not, right? We can take, for example, think of a quadratic function. If the quadratic function has 2 real zeros, which it could have, like what if I had x squared equals 4, then x equals plus or minus 2? Then that means there are 2 x-intercepts, okay? What if there's only 1? What if you had something like, let's say you had x squared equals 0. So x equals 0 is the only solution. Then there's only going to be 1 x-intercept, right? What if you had x squared equals negative 4 when you were solving your quadratic equation? Then you'd get x equals plus or minus 2i. Those aren't real solutions, so would those correspond to x-intercepts? No, that would be an example of a parabola that never intersected the x-axis, right? So then in that case, you'd have 0 x-intercepts, right? Only the real zeros correspond to the x-intercepts, okay? And we're going to hammer that again and again and again. So real zeros are the points at which the function intersects the x-axis. They are x-intercepts. What do you think about this one now? An nth degree polynomial can have at most how many x-intercepts? Well, the degree is n. I would think of a simple example, like think of a parabola again. What's the degree of a parabola? Show me with your fingers. The degree of a parabola. 2, right? That'd be an x, it's quadratic, so the degree is 2. What's the maximum number of x-intercepts a parabola could have? 2. So what do you think? If it's an nth degree polynomial, how many zeros could it have at most? N, right? Right? Because a second degree polynomial can only have 2 x-intercepts, right? A parabola can only at most intersect the x-axis twice. So always kind of think back to a simple example if you're not sure, if you can't remember. Okay, so then now let's do something here. Let's look at determine the number of turning points. And I don't want you to estimate. I don't really care about that. And I'm just going to say instead number of x-intercepts. So show me with your fingers, how many turning points does that graph have? 2. Good. Where are they? The turning points. Okay, so 2 turning points. And they are there and there. Okay. How many x-intercepts? Show me with your fingers. Okay. 1 x-intercept. Okay. And that one is right there. Agreed? No. No. I'm good. I never get tired of writing about math. If it was something else, maybe, but not math. Okay, so then now let's turn these into 2 statements. If we have 2 turning points, I want you to think about this. If there are 2 turning points, let's do one other thing before we do that. Sorry. I want to know whether the leading coefficient, A represents the leading coefficient. Okay, let me write that down just so we're clear. If A is the leading coefficient, I want you to tell me here, thumbs up for positive, thumbs down for negative. What must the sign of the leading coefficient be here? Yeah, good. It's got to be positive, right? How would you describe that kind of end behavior? Positive odd, yeah. But it's positive, isn't it? So A is positive. Okay, now, put on your thinking caps, right? I want you to really think about this. The fact that there are 2 turning points implies that the minimum degree of the polynomial, it could be like a really high degree polynomial, but what's the minimum possible degree that this polynomial could have if it has 2 turning points? Show me with your fingers. Yeah. Sophia, how come? You're right. 3 is correct. Okay, it's right. It would be 1 more than the number of turning points, wouldn't it? Because remember, the number of turning points, the number of turning points can only be at most 1 less than the degree, right? So the degree would therefore have to be at least 1 more than the number of turning points. Make sense? So this is implying that n would have to be greater than or equal to 3, right? Okay, what about the 1 x-intercept? If it has 1 x-intercept, that's telling us that the degree must be at least what? Show me with your fingers. Okay, the correct answer is, you're right. How come? Right, okay, so in other words, we said that the degree of the polynomial is equal to the maximum number of x-intercepts, right? Let's go back to the last page for just a second. Here's the statement, right? An nth degree polynomial, where is this? Is it on this page? Yeah, it is, right here. An nth degree polynomial can have at most n real zeros, right? You can't have more zeros than the degree of the polynomial. And again, think quadratic. If n is 2, the graph is a parabola. A parabola can have at most how many x-intercepts? 2, right? So the fact that it has one x-intercept is implying that n has to be greater than or equal than 1. Now, if both of those things have to be true, if n has to be greater than or equal to 3 and n has to be greater than or equal to 1, why do I have to use the word and? Let me ask you that. Think about and versus or. Or is not exclusive, right? Or means only one of the options has to be true at a time. And means each. When I use the word and, it means that both of the things that I'm using the word and to link have to be true at the same time. If there are 3 things joined by and statements, all 3 would have to be true. Have to be true, right? It's not an option for only one of them to be true. So for what values of n is n greater than or equal to 3 and greater than or equal to 1? Well, it will, okay, or equal to 3, right? Anything greater than or equal to 3. Does everybody get that? Right? Because wouldn't you agree, if n is greater than or equal to 3, then n is greater than or equal to 1. True? Okay, is true or false? Thumbs up or thumbs down. If n is greater than or equal to 1, is n necessarily greater than or equal to 3? No. What's a counterexample? 1 or 2, right? You see my point? So because this is an and statement, you have to take the most exclusive, right? We have to limit our degrees to being only 3 or greater. They couldn't be 1 or greater, right? We have to use the most exclusive of the 2 conditions, which is this one. Okay, so that's the degree would have to be at least 3. Okay. Now, is that consistent with the endpoints? Because that's the other thing we could do here is we could say, okay, n has to be at least 3. You guys told me this was positive odd behavior. Is 3 odd? Yeah, it is. Okay, so we're good, right? But what if these 2 statements told us that, what if we got the same 2 statements and we saw that this thing had positive even behavior? Then what would we say? Right? Like, let's just say hypothetically that we knew that we had the number of turning points was 3. Okay. The number of turning points was 3. Let me think about this for a second. He couldn't even do that, though, is the thing. You see my point here, though, I'm trying to make? It's kind of, I don't want to get, for reasons I don't want to get into, this wouldn't actually work. The calculus wouldn't allow this to work. But like if we knew that the function was even, let's say we knew n had to be greater than or equal to 3, but the n behavior was even, then what would the minimum degree be? 4, right? Because it couldn't be 3. 3 is odd. It'd have to be greater than 3 then. It'd have to be 4. You get my point? You have to put all these clues together. It starts to get a little complicated. Okay, let's try another one. Same stuff for this guy. And again, A is going to be, I'm going to change this. I think I got a little mistake here. So A is going to be determine the number of x-intercepts. And I don't care, I don't need to know I don't care about the coordinates of those for now. Okay, so part A, what's the number of x-intercepts? Show me with your fingers. Okay, yeah, it's 3, isn't it? Right? Where are they? Well, I mean, I can see one. There's an x-intercept. So one of them is at -2. Where's the next one? positive 2, and 8. Okay, good. Okay, determine, let's just skip up to C, determine the number of turning points. What's the number of turning points? Show them with your fingers. Yeah, wouldn't you agree there's 3 peaks and or valleys, right? There's a peak, there's a valley, and there's a peak. Yep. Okay, agreed? Pretty good? Okay, is A positive or negative? Thumbs up positive, thumbs down negative. Leading coefficient. Okay. How come, Hallie, you're right? Okay, yeah, what kind of behavior is that? Negative even, right? So we know that's true, okay? Now I want to know what's the minimum possible degree of this polynomial. Oh, I guess let's write this down here. So the number of turning points we said was equal to, or number of x-intercepts was 3, number of turning points was 3. So what's the minimum possible degree? Show me with your fingers. Okay, I'm seeing variation in answers. Let's break this down. I want to see if we can all arrive at the same answer here. What does this clue tell us? If there are 3 x-intercepts, that implies that the minimum value, the minimum degree of f is what? The number of x-intercepts is 3. That tells us the minimum degree is 3, right? Right. So n has to be greater than or equal to 3. Okay, if the number of turning points is 3, what does that imply about the minimum degree? Now think hard about this. If the number of turning points is 3, then the minimum degree would be what? Is it 2 or is it 4? Because I'm seeing, you know it's different, right? How come? Okay, and think about the parabola. The parabola has 1 turning point, but degree 2, right? Right? And the way you think about it is there can only be at the most 1 fewer turning points than the degree. The number of turning points can be at most 1 less than the degree. Okay? So this is telling us, that's telling us that n has to be greater than or equal to 4. So between the two, and we said n behavior was even, right? So combine all those clues. If n has to be greater than or equal to 3 and n has to be greater than or equal to 4 and the n behavior is even, what's the minimum degree? 4. Okay. Okay, give me 1 to 5. I mean, that's a lot. There's a lot coming at you there, right? Takes a little practice. Okay. Let's keep going. And this assignment, you're going to get lots of practice on this stuff. Okay, let's take a different approach to this. Now I'm not giving you a graph. Now I'm just giving you a polynomial. This will help. What's the degree of this polynomial? 8. Okay, so we see right away up here that n is equal to 8. What's the maximum number of real zeros the function can have? 8, right? 8. What's the maximum number of x-intercepts? 8. Real zeros and x-intercepts are the same thing, right? So this is 8. What's the maximum number of turning points? 7. 1 less. Okay, good. Right? Okay. If you think about, here's something that might help a little bit too. If I graph some function like this, you see that if I compare the number of x-intercepts to the number of turning points, oops, the number of x-intercepts is always going to have to be a little bit greater because the turning points can only be found between x-intercepts, right? I mean, that's not necessarily true. There could be, but if we're, let me say it this way, if the graph is not tricking us, if it's showing us all possible x-intercepts, so there are no imaginary zeros or anything, right? There's no hidden values for zeros or turning points or anything, then turning points could only occur between x-intercepts. Okay? Does that make sense? How do we know? You see what I'm saying? Okay. Right? So if turning points can only occur between the x-intercepts, doesn't that mean you're going to have one extra x-intercept than you are turning points? Kind of just think of it in terms of the picture. That helps a little bit. Okay, so now we're going to talk about multiplicity. Okay, and this is probably where we'll end up today. So the multiplicity of a zero is equal to the number of times its corresponding factor occurs. In other words, it's equal to the power of the factor. So all this stuff right here, that just means power of the factor. So let's say we want to find the zeros of f of x, right? If we want to find the zeros, it's asking us, what are the zeros, right? Well, that means we're going to take this function. I guess I can do it over here. And I'm setting it equal to 0 in solving, right? Those are the zeros. Well, how would I solve this equation, do you suppose? What do you think? I've got to factor it, don't I? The way we find zeros, if I can't point to a single variable, what did we have to do? Well, we had a quadratic formula, right? But this isn't quadratic, right? So we've got to factor this, okay? So we could factor out an x. Okay, let's do that. If we factor out an x, I want to see something here. Yeah, okay. If I factor out an x, what's left behind? X squared minus 6x plus 9, right? Okay, can you find magic numbers? -3 and -3, right? Okay, so we could do this then. I'm just going to scoot over. I'm kind of running out of room, but I'm going to scoot over here. So we could get x times x minus 3 squared equals 0, right? Anybody agree? Okay, so then what are my zeros? What's 1 0? Right? We're just using the zero product property. The only way factors can multiply and equal 0 is if I multiply by 0. So what's the value of x that's going to make the red factor 0? 0, yeah. Okay, so 1 solution is going to be x equals 0. Okay, what's my other 0 going to be? What's the value of x that makes the blue factor equal 0? 3, sure. Okay, what do you suppose the multiplicity of x equals 0 is? What's the power of that factor? Show me with your fingers. What's the power of the red factor? What exponent is it raised to? 1, sure. Okay, so because it's raised to the first power, the multiplicity is 1. Okay, see my point? What's the multiplicity of the blue factor, or the blue 0, 3? It's 2, because look, we had an exponent up here of 2. See my point? Okay, who cares, right? What's the big deal? They're just x-intercepts. There is a big deal. There is a big deal. This is helpful to us because it turns out that if the multiplicity of a factor or a 0 apply, there's same thing, right? They go together. If the multiplicity of a 0 is odd, then that x-intercept is going to cut through the graph, cut through the x-axis at that x-intercept. If the multiplicity is even, then the graph is going to bounce like a parabola, right? Because look what parabolas look like. Parabolas look like this, right? They bounce. They don't go all the way from positive infinity to negative infinity or vice versa. They bounce, right? So just like a parabola looks, that x-intercept is going to look like a parabola. It's going to bounce. So if I wanted to graph this thing then, right? Well, I've got it factored. Okay, well then what's that tell me? So I know that I would have one x-intercept at 0. Oh, wrong color. One x-intercept at 0. One x-intercept at 3. And what's my end behavior going to be? Show me what that picture is going to look like. What's my end behavior going to be? Or just describe it. Just look at the leading term, right? The leading term determines the end behavior. So positive odd. So it's doing this, right? Positive odd. So I know the end behavior because of that. The end behavior is doing this. Everybody agree? So now I just have to kind of put the clues together. We said the multiplicity of the 0, x equals 0 is 1, so it cuts like a line. And the multiplicity of the 0 at 3 is 2, so it bounces like a parabola. So the only way this could work then is if this function is going to cut through the x-axis there and then bounce right there. Make sense? See how we put all those clues together? And that's what a sketch of that graph is guaranteed to look like. Yes, sir.
How close is that, to the actual one? If you were to
It's well, I mean, I didn't graph it very well, but it's going to be pretty close. Okay, let's graph it and see. If I graph f of x is x cubed minus 6x squared, whoops, plus 9x. There it is. There's the actual graph. Here, I'll put it down at the bottom of the page. Okay, so it'll be in your notes. I mean, we got it, right? Does it look, I mean, so this is supposed to be, by the way, what we're doing here, what we're going to start to do is sketch graphs. We're not trying to graph functions. We're trying to sketch functions. If I want to graph a function, I'm going to use Desmos, right? But when we want to sketch a function, we just want to know what the shape, what the interesting behavior is. things like what's the nature of the x-intercepts. When we add calculus to the mix in a couple of years, we'll be able to know what's the concavity of the function, where are the inflection points where it changes concavity, where are the extrema based on the behavior of the first derivative. We'll be able to add all kinds of stuff to our sketches that we can't do right now, but we're starting the process that we're going to continue in a couple of years in calculus. Okay. All right, so now we can be a little bit, this is super cool. I want to just get through this one last part here. This is so cool. So I don't know if we'll get through it completely. Is this thing still working? Yeah. Okay, so now let's take an example like number 6, and that's the last one we'll do. So what are the zeros of this function? It's already factored for us. So what's the zero of that factor going to be? -7. Okay, so we got, there's 1, 0. What's going to be the zero of the middle factor? -1/2. Okay, right? Everybody agree? What's the zero of the left factor? +4. Okay, so those are our zeros. Okay, those are the x-intercepts. That tells us something important. That's where this graph is going to cross, going to touch the x-axis. May not cross. What's the multiplicity of -7? Show me with your fingers. Yeah, it's 2, right? Because look, there's a 2. Okay, that factor is to the second power, and so it is 2. Okay, what's the multiplicity of the 0x equals -1/2? 1, because that one's linear, right? It's to the first power. Okay. What's the multiplicity of the 0x equals 4? 3. Okay, so we would say that one is cubic. We've got a quadratic 0, a linear 0, and a cubic 0. Okay. What's going to be the effect? What's going to happen at the x-axis for the 0 with multiplicity 2? It's going to bounce. It's going to bounce like a parabola, right? What's going to happen at -1/2 where the multiplicity is 1? It's going to cut through like a line because the degree is 1. That's a linear polynomial factor, right? So it's going to cut like a line. And this is really cool. What's going to happen at 4 where the multiplicity is 3? It's going to cut like what kind of function? Like what? Like a cubic. Yeah, it's going to cut like a cubic. Okay, and when we graph this thing, that's actually what it's going to look like. Think there's a difference, right? If you're saying, well, what's the difference between a cubic cutting like a cubic or cutting like a line? Well, let's go back and see, right? This is what it means to cut like a line, go straight through. If it cuts like a cubic, it doesn't go straight through. It grazes the x-axis tangentially and then turns. See what I'm saying? It's got a distinct look to it. So our sketches are starting to look pretty accurate now. When we can start to even, yeah, tangentially. It just means it's gonna, if I zoom in, what it means is if I zoom in really close to the point where it crosses, yeah, if I zoom in infinitely far, it looks like the function is parallel to the axis. It looks like it's super, see what I'm saying? It just touches it at one point, but it touches it with the same slope as with 0 slope, okay? All right, so let's jump up and try to get a quick sketch of this thing. Okay, so what's this? If I go to the next page and we sketch this guy, we said we had an x-intercept at -7, so right there. We had an x-intercept at -1/2. That was the red one, right? The linear one. And then we had one at 4, correct? Okay. We said now the end behavior of this thing is what? The first term, I'm going to, like this is going to, if I expand that out, I'm going to get x squared is going to be my leading term of that factor, right? This one's going to be x cubed if I expand the whole thing out. This one is 2x. X squared times 2x times x cubed is 2x to the 6th, right? So there's the leading term. That's positive even behavior. So I know it's doing this, right? Okay, so I know the function is doing that and that. Okay, if it's bouncing, we said this was quadratic, so it bounces at the green. So it's got to do that. And then it cuts through the red like a line, so it's got to do that. And then it cuts through the blue like a cubic, so it's got to do that. And that's what it looks like. That's pretty cool, right? I mean, that gives us, wouldn't you agree, that gives us a pretty accurate, that's amazing that we can do that with that little bit of information, right? We've got some pretty critical pieces of the puzzle to be able to do the puzzle that easily, right? Okay, good place to stop.